The machining of parts is achieved using machine tools that bring cutting tools into contact with the workpiece. These cutting tools remove the unwanted material, shaping the part. Traditionally, the cutting tool's motion relative to the workpiece was controlled manually by a skilled machinist. But with the onset of mass production and the increased demand for part quality and uniformity, numerical control, or NC systems, were developed. These NC systems control machine components by converting programmed instructions into output signals. These output signals, in turn, control the machining process to produce a workpiece. Computer numerical control, or CNC, built upon the standard numerical control production capabilities by incorporating an integral computer processor to govern the machine controls. Programmed instructions, or data, in the form of a part program, is translated by the machine control into output signals that control machine functions, such as spindle rotation, cutting tool movement, workpiece movement, tool changing, and cutting fluid control. Computer numerical controls hold several advantages over standard numerical controls, including part programs can be manually edited on the onboard computer. Part programs can be run from computer memory. Workpieces requiring complex multi-axis machining can be produced, and machine and control diagnostics may be run, stored, and displayed during machining. These CNC advantages offer increased parts production flexibility, greater machining accuracy, and more programming versatility. The use of computer numerical control is widespread in manufacturing and is used in turning, milling, hole making, welding, electrical discharge machining, abrasive water jet cutting, punching, laser cutting, and many other operations. All computer numerically controlled machining begins with a part program. A part program consists of sequential instructions or coded commands that direct the machining of the part. Part programs are primarily generated by either manual programming of commands or, more commonly, by the use of computer-aided part programming systems. To understand how computer numerical programming works, first requires a basic understanding of key computer numerical control principles. The common factor that all computer numerically controlled machine types share is their ability to accurately and repeatedly control motion in various directions. Each of these directions of motion is known as an axis. Depending upon the machine type, the number of axes available for control commonly range from 2 to 5. Additionally, a CNC axis can be either a linear axis, with motion occurring along a straight line, or a rotary axis, with motion occurring along a circular path. Each axis consists of a mechanical component, such as a machine slide that moves, a servo drive motor to supply power for the movement, and a ball screw that transfers the power from the servo drive motor to the mechanical component. These components, along with the computer numerical control functions that direct them, is called an axis drive system. Because of the diversity of machine tool types and applications, this program will concentrate primarily on the basic computer numerical control principles of a vertical milling machining center. The vertical milling machining center typically has 3 linear axes of motion, with each assigned an alphabetic designate or address. The table's motion side to side is called the x-axis. The table's motion in and out is called the y-axis. And the head movement up and down the column is called the z-axis. If a rotary table is added on the machine table, then there is a 4th rotary axis, which is called the a-axis. The method of accurate positioning along each axis for all machine types is achieved using the rectangular coordinate system. On the vertical milling machining center, the horizontal baseline of the rectangular coordinate system represents the x-axis, and the vertical baseline represents the y-axis. The z-axis is at a right angle perpendicular to both the x and y axes. Increments for all baselines are specified in linear measurement. For most machines using the English system, the smallest increment is 1/10,000th of an inch. For machines using metric, the smallest increment is usually 1/1000th of a millimeter. The rectangular coordinate system allows the mathematical plotting of points in space, called coordinates, among 2 or more machine axes. Each coordinate is an actual physical location that the machine is instructed to move through. These coordinates indicate the position of the cutting tool center and are collectively called the tool path. The location where the rectangular coordinate baselines intersect is called program 0. It is also known as work 0, part 0, or the part origin. Program 0 is the common or reference point from which all coordinates are derived. The placement of program 0 can vary from part to part, but is generally located at a part surface from which other coordinate dimensions are referenced. The 2 programming modes of specifying coordinates within the rectangular coordinate system are the absolute mode and the incremental mode. In the absolute mode, the input values of all program coordinates and their polarity, that is, whether the coordinates are plus or minus, are specified relative to the program 0 point. In the incremental mode, the input value of each current program coordinate and its polarity is relative to the previous program coordinate position. The differences between the absolute mode and the incremental mode are apparent when comparing the calculations used for each mode to generate the same part. Of the 2, the absolute mode is more widely accepted by CNC users. All CNC controls assume coordinate values to be plus unless a minus sign is specified. Additionally, if a coordinate falls on a baseline, its value is 0 and the coordinate has no polarity. The rectangular coordinate system is segmented into 4 quadrants to help establish a coordinate's polarity. Quadrant 1 represents the plus x and plus y coordinate position. Quadrant 2 represents the minus x and plus y coordinate position. Quadrant 3 represents the minus x and minus y coordinate position. And quadrant 4 represents the plus x and minus y coordinate position. To better illustrate a coordinate's polarity within the rectangular coordinate system, let's assign the center of this bolt circle as program 0 and examine the position of the bolt circle's 8 coordinates relative to program 0. The coordinates in quadrant 1 all have plus x and plus y positions. The coordinates in quadrant 2 all have minus x and plus y positions. The coordinates in quadrant 3 all have minus x and minus y positions. And the coordinates in quadrant 4 all have plus x and minus y positions. An awareness of these basic computer numerical control motion principles is essential in the generation of part programs. For any computer numerically controlled machine to function, it must be instructed on what to do. Instructions are provided to the machine control in the form of part program commands. When run, a part program is interpreted one command at a time, sequentially. The machine control receives the first command and executes it. It then receives the next command and executes it. The control continues executing program commands successively until completion. Part program commands, which are also referred to as blocks, are composed of words. These words all begin with a letter address and end with a numerical value. Each letter address specifies a certain function that the machine control will perform. Two of the most important letter addresses are G and M. The letter G, along with its numerical value, specifies preparatory functions. This allows various modes to be set to prepare the machine.